questions as clear as I can. But I don't want to spend too much time on any aspect, you all understand. So for this problem, I forgot how many. We had, what, Zinfandel, we have 4, and is it Merlot 5 or 6? Is it 5 or 6? 5? And cabs, is it 7? 6, sorry. So the total number of wines is gonna be, what, 15, right? 15 wines, and really, you can expand this. You could have like M, N, and J or something like this, and the sum of these is the number. That's all it is. First part, I think they asked something about the Zinfandels. How many ways to take 2 if order is important? Is that it?
Yes.
All right, and I better put this up. This for permutations, and I use K of N. In the answer that's provided, they use N of K. They put the larger number first. Y'all follow me on this class? It's just the way they do business. So for N of K here, this is really going to be N factorial for permutations, N minus K factorial. For combinations of K over N, you need to know this one. It's going to be N factorial over K factorial, N minus K factorial. And this is where order is not important. You all clear on that, everybody? All right, so if we do this for the first part, it's for the Zinfandel, how many ways to take 2 out of the 4 if order is important? Y'all hear me? That is a permutation. Does everybody agree? So for that one, it's going to be this, and I'll just put it down. So there's 4, it's going to be 4 factorial, and it's going to be over 4 minus or 2 factorial. So that's going to be really 4 times 3 and over, yeah, just 4 times 3 or 12. Is that right, class? Mm-hmm. All right, what's the second part of this?
It's just, if you take 6 from the 15, how many ways are there to do?
All right, now here, they specify nothing about what the content. They just say, if you're gonna take 6 of the 15, forget their 3 wines. You all with me on this class? Just 6 of 15, and order is not important. Unless they say order is important, assume not important. For this one, this is really gonna be a combination, and it's gonna be 6 of 15. Now your calculators, have you tried this on your calculator? You should have a function. How many saw a function that you could just punch these things in? If you didn't, you have one, believe it or not. I'm almost positive if you have a modern calculator, you have it. Who has found that function? Did you say you did? You didn't? What kind of calculator?
Inspire.
Anybody else have an Inspire? You don't have one?
I got a 36X.
All right, tell you the truth, I think every modern calculator that has a statistical package should have something that equates to a combination and a permutation. And also for binomial distribution, for the probability stuff that we get to. Okay, for this one, it's gonna be, since this is a combination, it's 15 factorial, you tell me if it's right. And this is gonna be over 6 factorial, and it's gonna be 15 minus 6, so it's 9 factorial. So I'm just going to say that's really, cancel this and this, and I have 15 times 14, 13 times 12 times 11 times 10 over 6 factorial, which is 1 times 2. I'm trying to see what I can cancel. Can somebody just give me this real quick?
5,000.
Is it 5,005? I remember that, I think. And that should be, I mean, it should work out. I didn't do the math on this. Did you check that to make sure it's okay? All right, part 3 is what?
It's, if 6 bottles are randomly selected, how many ways are there to obtain 2 bottles of each variety?
All right. For this one, order is, what did you get?
I just found the function I was just showing.
Which kind?
On the 36X Pro.
Oh, we do?
Sure,
Yeah.
sure. Go ahead, you can take it. All right, two bottles of each, and order's not important, right?
Doesn't specify.
All right, so here, what we're gonna get is probability of A times probability of B times probability of C, because they're disjoint. Y'all follow me on this class? Now, I didn't get into disjoint. Did you read about this in the reading I gave you? Okay, there's disjoint. Joint would mean they have common elements. Like if you had a Merlot / Cabaret that had a bottle that's in both of those two bins, that would be a non-disjoint group. If they have nothing in common, they're disjoint. So now what we're really talking about, if we talk about this, two bottles of each, right? So combination. So this one is going to be probability, and I'll just say two of each. So it's going to be, first is a combination of the Zinfandel. So here, you're going to have 4 factorial over 2 factorial times 2 factorial. You're going to have to help me with this one. That's the probability of the Zinfandels. Then it's the probability of 2 from the Merlot, which is 5 factorial over 2 factorial and 3 factorial. And then of the Cab, which is going to be 6 factorial over 2 factorial, 4 factorial. And I don't know what that is.
900.
Say again.
900.
Is that what that comes down to? 900, okay. All right, 34, what's the fourth part? D, part D, part D.
If 6 bottles are randomly selected, what is the probability that this results in 2 bottles of each variety being chosen?
All right, now, I think it's discussed, but they say 6 bottles are selected, right? Now, you gotta think of it like this. Here's the event, 6 bottles. All right, I'm just saying this whole event space, you can call it A. Now, a subset of that, remember, that's the event space, right? If they are selected, and this is probability or just numbers? All right, now probability is going to be ratios of areas. Think of it that way. I'm trying to make sure I say this, and I'm going to spend a little more time on this in a second. So I'm going to say B is worth 2 bottles of each. All right. So you can think of this as a partitioned region where you've got 2, 2, 2. You all agree this is a smaller subset, right? But we have that information, don't we? We have that number from right there. Y'all with me? And that's the key to this. You gotta see that if we take 6 bottles, they could have 4, 1, y'all with me on this? But there's a subset that just has 2 bottles of each within that. It's a much smaller subset. And what this problem's trying to get you to do is see the ratios. So in effect, the probability would be this area, or this number, divided by the total number. Does that make sense to everybody? If you understand, can I say your hands if you understand? I want to make sure you understand this, because a lot of people see this, and then a quiz comes, or a test, or something, and they just don't know what to do. But it's always ratios of area. That's what I try to say. It doesn't mean just planar areas, but that's the way I think of it. It's easy to visualize. So for this one, well, probability of 2, 2, 2 of each is 900, isn't it? We have, yeah, 900, right? And the way you can take 6 bottles from 15, which was the original, the 15 is the omega space, is 55,005. What is that? I don't know.
It's like 18% pretty much?
What?
Like 18%?
0.18. We can use percentage, but I prefer that right now. It's a fractional area. Y'all with me? Now what's the, that's 4 or part D, all right, part 5 or part E, which you asked about. What does it say?
It's if 4 bottles are randomly selected, what is the probability that all of them are the same variety?
Okay, now, based on what I just said, right, here's 4 bottles. right? Do you all agree within that, there is something, a partition region, where you have 4 of each? Do you agree with that? Are you with me on this, class? Well, actually, I'm saying this in a bad way. It's like, no, that's not. If you have 4 bottles selected, the probability that they're all the same, remember you have 4 bottles. So in that problem, what did you ask specifically? I'm trying to answer your question carefully.
I was just wondering when would I multiply probabilities to get like a number or add them together? Because in part E you add them together, but in part
Yeah, but read the question. It says, what is the probability?
yes, what is the probability that all of them are the same variety?
All right, now I'm going to try to say this with words first. And when I go through the lecture today, hopefully I'll make it clear. So if you have those bottles and you select 4, right? Say the probability of getting 4 Merlots, right? What would that be? Just 4 Merlots, if you take a look at that, if you selected them, how would you do that? Let me ask you this, what's the probability of getting 1 Merlot?
1 out of 15.
Pardon?
1 out of 15.
And 2 Merlots?
Or I guess
3 Merlots? 4? What are you really doing? Here's the problem you're having, I think, because I can almost bet you do. So you're wondering, there's less Merlots than there are other things, right? And the way you think of it is go to the extreme. 1 Merlot, 14 others, right? What's the probability if you select one, you get a Merlot? It'd be 1 out of 15. Does everybody see that? What if there are 2 and 13? 2 over 15. 3, okay, yeah, sorry, 2, yeah, I said it. So then you can work down, right? The probability of selecting 4 out of 15 would be what? 4 divided by, what's the total number? 15, right? So it would be the probability of getting that. What's the probability of getting 5 or 4? I mean, that was Zinfandel, sorry. For the Merlots, there's 5 of them, right? Probability of getting, actually I'm saying this and I'm not specifying it clearly. I need to show you this set theory. One second, for that one, does it give probability of just 4 Merlots plus probability of just 4 Zinfandels plus probability of, that's the way to do this because they're disjoint. But what is the probability, and I think you saw it for one Zinfandel from 15. If there's only 1 bottle Zinfandel and all the others are something else, it's 1 out of 15, right? 2 Zinfandels in that same, what I'm trying to do is say 2, and then the remainder is going to be other wines, doesn't matter what they are, right? So just grabbing one would be 2, right? So if we want the probability of getting 4 of those, right, of selecting 4, right? Think about this. Try to do this, and it's not coming out quite the way I want, but I'm going to work on it. What I'm really trying to show you is this permutations, the actual way he does this, because this is combinations. Actually, we can just use the combination formula for this. So we can say, for the Zinfandel, the probability of getting 4, and this is going to be 4 factorial, 0 factorial, because this is going to be combinations. That's just the Zinfandel. First, do we all agree with that? That's going to be the probability of just, or I should say, that is the number of ways. Do you agree with that? And then plus, and then it's going to be 4 factorial, or sorry, 5 factorial. I think this is how he has it, but I don't remember. over 4 factorial 1 factorial plus 6 factorial over 4 factorial 2 factorial and now if we have this, we have to divide this, because these are going to be the number of ways, right? Then we have to divide this by the probability of getting 4 from 15, correct? Or the number of ways. Do you all agree with that, class? So this is going to be 15 factorial over 4 factorial, and this is going to be 15 minus 4 factorial. And that should be the probability, because it's the area. I didn't say this quite the way I want, but what I'm really getting at is the top part are disjoint. So you add up the possible numbers. The bottom set is something where you don't care about what bottles, it's how many different ways you can take without ordering from that group if you have 15 bottles. Does this make sense? I didn't get into the ratio of probabilities yet. Is that the right answer, by the way?
Yes. Yep.
But what is the answer? It's something low.
It's 0.0154.
Is that right?
Yes.
All right. But that's the way you do it. Now, where it gets confusing, I was trying to do this in a way that makes rational sense. But in the book, he goes through the way the actual permutation comes about. He does a proof of it and the combination. Because with the combination, since order is important, they discount every time you have the same exact values, regardless of the order. But they do it in the book, and they do it pretty exactly. The guy's good. Now, let me go through a set there, and this should help. Here's where I personally have trouble. Like in my mind, I understand this, but explaining it is, when you think about these problems, is how to visualize anything going on. And I always go to the extremes. I don't care how many different lines or anything like that, or different objects. The only thing I think about is the extremes. If all the other objects in the set are something else, then there's only one object. So what's the probability of me grabbing randomly and getting that object? So always just whatever, 1 over however many there are. And that's it. And the way you do is to slowly build on that. You should be able to see it. But it does get confusing, especially if order is important, because then these become permutations. Okay. In a nutshell, that's that problem. It's a pretty good problem, and it's a classic problem. I didn't talk about the set theory in areas I'm about to. This should help what I'm about to do. Read the book, and I hope you did. He does a pretty good job explaining this. One thing I didn't realize when I asked him to read the problem last time, it wasn't discrete values inside the intersection. It was a line. It was a continuous line. I'm going to do that one too. But with set theory, I want to go through this, and he talks about De Morgan's laws. What I worry about, what I consider is most important is to see this visually, and you'll understand. So if I just say, and I'm doing this for your good, because you're going to get something like this on the quiz, so you might as well be attentive here. If I say A is 1, 3, and 5, and that's it, and I say B is equal to 2, 3, and 5. Now, just going through the basics. Remember, I did not say what the total region is or all possible outcomes. These are just subsets of something. It has nothing to do with the total. So if I look at this and I say A union B, what are the values? Just look at it. And I'm using these curly brackets because he does. 1, 2, 3, 5. Yeah. 1, 2, 3, 5. He makes a point in his discussion. You can't have 1, 1. Suppose, I mean, obviously, if I had a 1 here and a 1 here, 1 would be part of that, but only one time. It wouldn't be repeated twice. That's one point he makes. To me, that's a silly point. Right? When we're talking about this, we're talking about all possible values that appear in both of them one time. Then if I have A intersect B, it's the common elements, correct? And if you look at this, what are they? Pardon me?
3, 5.
Just 3 and 5. Now, if you visualize this as A and B, this is visualized as A intersect B, right? I'm trying to show you this visual. Now, if you look at this, if you actually look at this and we talk about the probability, now I'm going to introduce probability, the concept of probability based on kind of the area ratio. And in his discussion, he talks about the region omega. That's all possible things that can happen, basically. It doesn't matter if it's continuous or discrete space. It doesn't matter if they're talking about yellow, red balls or A, B, C or anything like that. It's all possible things that make up the outcomes we're talking about. Then he talks about an event. Now he uses the word event. I generally don't do, but the event would be 2 red balls, 1 blue. That's a definable event. Follow me? And it has to be just that. So that would be an event, a probability of an event we'll talk about. And then he also talks about discrete and disjoint. Or sorry, disjoint and adjoint, or things that are non-disjoint. Disjoint means they have nothing in common, A and B. Anything else is adjoint, or there's common elements, there's common outcomes in both events. Follow me on this, guys? It's just terminology, but you have to at least appreciate. So when I look at this, and now I'm going to talk about probability. So now I'm going to introduce something, and I call this all possible outcomes. The symbol he uses is capital omega. It just means everything that can happen. Every possible outcome is included in this. A and B are subsets. Y'all follow me? Now I'm going to say the probability of A occurring is definable as the area of A over omega. Think of it that way. It doesn't have, it's very hard to imagine area when they're discrete values, but it has to do with a numbers game. The numbers of outcomes in omega versus the outcomes in A, the ratios do. Does this make sense to people? Think of it that way. And you can call it, I hate to do it this way because this is very inexact, but think of it A over omega. Then probability of B, and these are fractional probabilities, not percentages, is going to be B over omega. Now, before I continue, I'm going to say one other thing. And these are just, to me, they're obvious, but he states them explicitly. When we talk about the probability of an event, it has to be between 0 and 1. 1 means it's going to happen. It's impossible for it not to happen. 0 means it's never going to happen. But it cannot be negative. Y'all follow me? It cannot be negative. And if you talk about disjoint sets where A, B, C, D are separate, all right, they have no common elements, then the probability of A plus the probability of B plus the probability of C plus the probability of everything else has to be 1. More or less, if you're rolling a dice, something between a 1 and a 6 that's a discrete value is going to happen. It has to. That's the only possible outcomes that we allow. You can't have the dice just on its edge, not falling. It's an assumed outcome that's discrete. If you have a continuous number line between 0, including 0, between 0 and 1, that's all possible values between 0 and 1. Fractions, it doesn't matter. Any possible value, it's inclusive. That is an infinite set, and it's not countable. Do y'all follow me on this? It's just a way to be very exact mathematically. Here, if you appreciate this as an area kind of thing, it's not real area, it's what it is how many things there are, or events, I don't like the word event, how many elements there are in A over omega. That's really a better way to say it. Now, this is one of the laws that you have to understand. When I saw, this is called conditional probability, and this is very important that you see this because it'll help you immensely. And I need you to be attentive here. The way he covers this in a book, I don't like, because he gets really into the weeds with some of the mathematics, symbolism and stuff, and it kind of covers over the simplicity of this. If I say the probability of A and there's a slash B, it means probability of A given B occurred. It's assuming B has happened. Y'all with me? That's what that slash means. How many read that in the book and saw it? Do you remember this? That was part of the reading. Now, you need to know this really, really well. Not right now for the quiz, but you need to know this. This will help you immensely. Now, when I say that, remember I told you about the ratio of areas is the way I think of it. So, the probability of A given B occurred. Now look, I want you to see this. It's saying B happened. This event happened. Can y'all follow me? And what he says, if that event happened, any event in here or out here can't happen. You follow me? It's saying this happened. If that happened, what is the probability of this event happening, of A happening? See that little sliver of land there? So what that is this. It's going to be, and the way you write it mathematically, it's a couple ways, but would be the intersecting area, right? You should be able to see this over the probability that B occurred. You all follow me on this? Just look, it's ratio of areas. It says now our problem becomes B occurred. Here's the total space of all events possible. Now, follow me? And what is the area, and I hate to use that word so simply, but it's true. The area that this event occurred, it's just the ratio of what? This area to the total area that is guaranteed to happen. Follow me? Now, this is important. When you look at this, what would the probability, here I have probability of A given B. I'm going to show you De Morgan's law in a very simple, or I should say Bayes' theorem in a very simple way. Now, let's take the probability of B given A. All right, it says A occurred. Just watch this. I think you'll see this. It'll help. So now it says A occurred. I guess I should erase that. I almost don't want to, but I will. I'm going to redraw this for everybody's sake, including mine. So here's A, and here's B. Here's A intersect B. And I want you to take a look at this for 1 second. Bet you can get it. Remember I told you it's a ratio of areas. So it says A occurred. A occurred. This thing occurred. And I want the ratio, if A occurred, B will occur. Y'all follow me? Here's B within that region, right? So that becomes right? That would be the intersecting area over the probability of A. How many? This is called Bayes' theorem. You're going to see it. It's a very simple way I'm doing it. I'm not trying to make this more complicated than it need be. Now, one thing you can see in common with both of these is this. That intersecting area. Do y'all see that? What we do here is, this is equal times P of A, probability of A. You can cancel that, right? Over here, I'll multiply this times probability of B. Y'all with me? Now I'm going to equate this to that. And I can say, if I look at this, the probability of A, I'm taking this one, times probability of B given A is equal to probability of B times the probability of A given B. And that is called Bayes' theorem. And I want to tell you something else about this. It'll become very obvious after a while, but you're going to have to kind of work with me on this one and remember that, put it like to your memory, but remember where it comes from is these Venn diagrams. That's why they're so useful. Because if you see this, you can get any information from that thing. If I say, and I'm going to ask you some silly questions. What is the probability that A unit or A intersect B does not occur? Now, what would that be? Just think for a minute. You can see it area-wise. If omega is this whole space, right? The probability that it doesn't occur is what? It's just the whole space minus that. I mean the area. Can you all see that? That's the simplicity of it. Mathematically, we can get into all sorts of things and talk about a lot of stuff. Let me show you some of the stuff. So, here's a couple of more things that happen based on that illustration, that Venn diagram. There's a lot of different ways to express this. I think these are, I believe these are De Morgan's laws, I believe in the book. So if I take a look at this, and remember I'm using this, where A and B have overlap, I can say that the probability of A plus, let me get back. Sorry, let me do it this way. The probability, now listen to me on this one, of A union B. This is not an intercept. Y'all with me on this? Just watch. It's just, you don't see how useful this is. What I'm really saying, the probability of A intersect B, that's this whole area here, right? Now follow me on this one, please. You'll see it. That's really, now just listen, it would be the probability of A and the probability of B. And if the two were disjoint, if they had nothing in common, that would be it, right? But look, if we take this and add to it this, the probability of this, we've actually included this twice. Y'all see that? So we have to subtract it one time. With me? So now you have to say that plus that minus the probability of A intersect B. And that would be the probability of A or B occurring. Y'all with me on this? And it should make sense in terms of the areas kind of idea. Everybody with me on that? These are useful. How many remember, did you read De Morgan's law on this one? Anybody? All right, now the way I'm showing you, I think gives you a better idea of how to get a handle on that. Just memorizing these things will get you in trouble in my opinion, because here's the extension of it. The logic of this extension is, why just two? Why don't we have n of these? Like A1, A2, A3, all down the line. All of them are possible intersections. You all follow me? Then this gets mathematically it becomes clumsy. It's large in the statement. But the essence of it is this. Y'all with me? And if I added one more just to show you what I'm talking about. If you had C. And you can see this little area is the area that they all intersect, right? Now listen to me. Y'all can see, you would start by saying probability of A plus probability of B plus probability of C, right? And then you got a problem. For A and B, right here, you've added this sliver one more time than needed, right? So you'd subtract off that. Y'all with me? And then for this one right here, you can just take the extension of it. I'm trying to, how would I do it? Basically, you would have to take this plus this and then subtract off the intersection of B and C, right? And then finally, B and A, you would have to take, or B and C, or A and C, pardon me, you would take, basically, you have to take this and this, which we added already, and then subtract off that common area. Can everybody see this? This is the extension. Let me see where this is in the book and give it to you because I think it's valuable. And I'll give you problems that are related to this that'll help you. So, this is over to the left. He has a lot of things to say. Some of the problems he gives in the beginning are a little much. Okay, so this is on page 78. This is a corollary, a union of two non-disjoint sets for A and B. And I'm looking for his extension for n sets in here. Okay, so this is on page 90, and it's example, I believe it's example 2.47, just write this down. And the problem with this is stating some of these things in terms of mathematics, where you have the summations and they go to infinity, doesn't let you see the essence of what's going on in my opinion. It's better to say, I got a few other things I gotta cover. You all with me on this one? I'm trying to get through this before I just give you examples. I'll go through the functions next time. I don't think I'm gonna have time. You might want to write down, try exercise 2.46. I'll do it if I have time. It's exercise 2.46. And I tell you, I don't like this because he makes it a complicated event. He says if you have first a die that has only 4 outcomes, 1 through 4 instead of 1 through 6, which is kind of weird. Then if he says if the first roll is X, second roll is Y, he defines event B as the minimum of X, comma, Y, one or the other equal 2. Now already he's complicated the simplicity of this. He says you got 2 rolls, and he's defining an event as a minimum of 2, which means it could be 2 or 1, 2 or 1. You all with me on this class? Or I'm sorry, it could be 2, 3, and 4, 2, 3, and 4 on either of those rolls. So the probability of a 2, 3, or 4 in the first roll is 1 event, right, just by itself. That would be 3 out of 4. You all with me? Then he says, and the probability of basically that the second event would be 3 out of 4, but it'd be squared. But he's making it way too complicated. Then he says M is the maximum of X and Y, being either one of those two being 3. So that means it could be 1, 2, or 3. First roll, 1, 2, or 3. Second roll, you all with me? Same number of elements, you all with me? But then he says, find the probability that M is going to happen given B happened, and you got to graph that. He does a good job showing you, but that's a more complicated problem than you should start with. Just remember that, what I just told you, as best you can. So I'm trying to let you know this book is going to have some problems that right off the bat are going to tax you. They're going to be more difficult than they need need be to see what he's talking about. You can get there, but this is, I don't like that he goes right into the depth he does sometimes. I did base theorem, now I have to get through this communication channel. If you wanna know where this is, it's the bottom of page 91. This is a good problem. Please write this down, star it. This you're gonna see over and over again, we're gonna talk about it. And the reason is it's conditional probability actually applied to something that's a real communication channel. It's only two channels. It's, I should say, two inputs, two outputs. When you extend this to n inputs, n outputs, it's called a multiple input, multiple output systems. And it's valuable to understand this. Okay, for this one, does anybody have the actual book here besides me? You just have PDFs? Okay. Who's recording your Elijah stuff? There you go. Bottom of there, you're gonna see a communication channel. Let me just show you this and I'll ask him for some stuff. So here, you're gonna see these kind of lines. These are, what does he call these? S, send a 0 and send a 1. So this is a 0 being sent, and this is a 1 being sent. This could be a 5-volt 0 system. It could be anything. It could be a -5 is a 0, +5 is a 1. It doesn't matter what it is. There's a 1 and a 0 being sent. And then he's going to have this. He's going to say that if a 1 is sent, the 1 has a probability of P being sent. Here, he's going to say, if that's P, the probability of a 0 is 1 minus P. Now this is in your book. P is a probability of 1. 1 minus P, you can call it Q if you want, is probability of a 0, whatever that means. It doesn't really mean anything in terms of an actual voltage value or something. It just means this is what we consider as the two possible inputs. He says if a 0 is sent and a 0 is received, these are receiving. So he uses R0, meaning a 0 is received, and R1, meaning a 1 is received. And this is the possible flow of the signal. These down here. So you got to help me on this. I think he says as if a probability of a 1 being sent and a 1 received, that this is going to be N, is this what he uses as the weight?
Yes.
As a,
Yes.
okay, now what that means is that if a 1 is sent, and the way he phrases is a little weird, but he's saying the probability if a 1 is sent and 1 is received there is N. Y'all with me? Does he use eta?
Yeah, it's eta. He has 1 minus eta on
The
1 to
diagonal.
receive 1. No, horizontal. The diagonal.
1,
Yes.
1, 0.
1 to 0, he has eta.
Oh, okay, so he's using this as an error. So this is going to be eta, so this would be a probability of an error, I guess. So eta is a probability of error if a 1 sent and a 0 is received. And here it's going to be 1 minus eta, so eta is small. This is the probability if a 1 is sent and 1 is received. Eta is the error rate, or error. Here, this means this will be epsilon, so that's the probability. If a 0 is sent and a 1 is received, that would be an error. Y'all with me on this class? Here, it would be 1 minus eta. Now just get a handle on what I'm really saying. Regardless of what's being communicated, this the statistical kind of information is useful. If I try to send, the likelihood of sending 1 is P. If I send a 1 and receive a 1, it would be P times 1 minus N would be the probability of sending a 1 or receiving 1. Y'all with me? Hopefully it's large. The probability of sending a 0 and receiving a 0 would be 1 minus P, whatever that is, times 1 minus epsilon. With me? And by the way, this probability of sending a 0 and receiving a 1 would be epsilon times 1 minus p. You all with me? So now he's going to ask for a few things. And he's trying to use the conditional probability that I just talked about. He's going to apply that law here to get information, a probability of a 1 is sent and a 1 received and so forth. But first thing he does, he says, what's the probability of receiving a 1? Now, I bet you can get this if you think about it. And just listen to me and work with me on this one. This is over at 11, right? I want to finish this, just let me finish this, and you get your quiz, and I'll give you all the time you want. If I take a look at this, receiving a 1, here's a 1, right? All right, the first way I can get a 1 is probability of a 1 being sent, which is p, times 1 minus n, or eta. So that's the probability of receiving a 1 if a 1 sent. Do you agree with that? What else? There's also 1 minus p. Now that's the probability of a 0 being sent, correct? With me? Times n, right? And that's the probability of a 1. Do you agree with that? Now, what does he ask for? Now, I don't see how many of these I have to. I can get the probability of a 0 too. What does he ask?
Just that, and then
Now, first of all, do you all agree with that? And that's it. Now, if I have the values for p and eta, I can get this. And I probably can fuss with that to get it in a different form, but that's it essentially. Go ahead.
and suppose that we've received 1. What's the probability that 1 was originally sent?
So now he's talking about what's the probability if a 1 was received giving a 1 was sent. Y'all with me on this, class? Now this is basically Bayes' theorem. Y'all with me? So think about what I wrote up there, where I had P of A times probability of B given A is equal to probability of B times the probability of A given B. Remember that? How many basically remember me putting this up there? I used what? The intersecting area probability of A intersect B, and I found basically where I could just equate these things through the use of that. So now I come over here. So I know that based on that, this is equal to the probability of sending a 1 and receiving a 1, right? If you look at the way I've done it, divided by the probability, or I should say, let me do it this way. Sending 1, receiving a 1 times the probability of receiving a 1 divided by the probability of sending a 1. Do you agree with this? I took the probability of A and associated with sending a 1, and the probability of B right there as receiving 1. Do y'all follow me on this? Just take a good look at this and please just try to appreciate what I'm doing. I'm trying to make it simple. Isn't that what you see in the book? I don't care if he uses different symbols.
I think he does the notation the other way,
I
but
don't
it
care.
looks the same.
I don't care. Notation doesn't matter. These are just symbols. Come to here and let's do this. First of all, what is the probability of sending a 1 and receiving 1? Why don't you just look at this? Well, sending a 1 and receiving a 1, it would be 1 minus 8. Do y'all see that? So sending a 1 and receiving a 1 is 1 minus eta. And what's the probability of receiving a 1? It's that, right? It's all, that whole mess right there. And then its probability of sending one is P. And does he have the probability of sending one, receiving a one, or receiving one, sending one? I think I did the opposite way once. Let me think. It won't matter if you understand Bayes' theorem, you can get, this is, you might have sending one, receiving.
Yeah, you might.
No, he has probability of sending one, receiving one. I've done the opposite. I've inverted it. So he wants this. We can do this, I think, in a second. He has the probability. So what he's saying is the probability that a one was sent given a one was received. You with me on this one, class? That's the way he states it. That's, and by the way, he can ask for anything. So a one was sent and a one was received, given a one was received. So that's going to be equal to the probability of receiving a one given you sent a one times the probability of sending a one divided by the probability of receiving a one. Do you agree, first of all, with the structure? The terminology R1 is receiving one, S1 is sending one. Anytime you get something slash something, it means the something under the slash has happened. Now follow me on this. So what's this going to be? Well, the probability of receiving a one, assuming a one is sent. I have a one, I send it, receiving one is just one minus that. Y'all follow me on that? It's just one minus eta. It's one minus eta. And then I have to multiply that times the probability of sending one, which is P. First, I want to make sure you're seeing what I'm doing. Y'all with me on this, class? If I put actual numbers there with 25%, this thing would get kind of complicated quick, but the essence of what I'm showing you is, so it's times P. That's this part. The probability of receiving a one is that. And that's going to be P times 1 minus eta plus eta times 1 minus P. Now, that's exactly what he has, I believe. Oh, wait a second. I forgot. This should be epsilon. I had eta there. So this should be epsilon. But it is in the book. But that's the way this link works. A simple communication link. And you configure anything you want. Usually what they want is the probability of a one was sent if a one was received. They want to know that. They want the probability that a zero was sent if a zero was received. Those are two things that are very important. And what they want is the sum of those two is the probability the channels function. Y'all with me? We'll get to ways of doing this problem later. I got to give you a quiz now. So what I'm going to do is ask you to separate yourself. First, can I get, let's see, this row, could you guys move to that side? You guys can stay in that row, then you three move to this row, and can I move you in the back and maybe you in the front? Doesn't matter, I'm trying. The essence of what I'm doing here is try to put a